Welcome to AP Environmental Science. This PowerPoint is for global wind patterns and oceanic currents. This PowerPoint is going to cover two learning objectives, topic 4.5, which are global wind patterns. For this one, we're still in the same enduring understanding as we were for the last couple PowerPoints, but the learning objective is to explain how environmental factors can result in atmospheric circulation. We'll talk about what that means and we'll talk about those patterns. For topic 4.9, that's El Nino and La Nina. The enduring understanding for this one is a little bit different. Most of the Earth's atmospheric processes are driven by input of energy from the sun. So the sun is the ultimate source of energy for most of the weather patterns on the planet. The learning objective describe the environmental changes and effects that result from El Nino or La Nina, both of which are in the El Nino Southern Oscillation Cycle. The vocab I'm going to skip as usual, but you can pause this now to copy it down. So to start with global wind patterns, we're going to start with what is wind? Wind is essentially just the movement of air, and it results from differences in temperature. Okay, so you're going to have differences in temperature, which result in differences in pressure, and that's what's being shown in the diagram. We have a high pressure area and a low pressure area. And in those two pressure systems, there is going to be movement of air. In this high pressure system, we have cool air that is moving down, cool dry air is going to descend, and then that hot air down below is going to move over towards a low pressure system where it will rise up and cool. All right, so that movement from this high pressure to low pressure is what we experience as wind. All of this is wind, but this is ground level, so it's really what we experience as wind. So the differences in pressure are going to create wind, and air will always move from areas of high pressure to areas of low pressure. And it's just like if you're talking about concentration gradients, things are going to move from an area of high to low. So high concentration and low concentration, in this case, it's high pressure to low pressure. Okay, that creates a pressure gradient, and this entire system is trying to reach equilibrium, just like most things in nature, trying to reach equilibrium. Okay, so if we were to use an example of a pressure gradient and air moving from high to low pressure, what happens when you open an airplane door if it's at altitude, right? The air pressure inside the plane is relatively high compared to the very low pressure that is outside, and everything that is inside of that plane gets sucked out. It moves from an area of high down to an area of low. So that's wind. We're not really going to focus on what is wind too much. We're going to focus more on climate in this class rather than weather. So we're not too interested in day-to-day wind patterns. But what we are interested is the big picture, the entire Earth system as a whole. Okay, so one of the things with the Earth system is that Earth is rotating on its axis. You can see that on this diagram right there. That represents the rotation. Okay, the Earth is rotating on its axis, and the air that is surrounding the Earth, that's gravitationally bound to the Earth, is not attached to the Earth, right? It's not like the land itself that's attached. The air is not attached. It moves with it, but it lags behind it. So say that we were to have wind that was trying in a hypothetical situation to move straight north. That wind isn't going to move straight north because the Earth is rotating along its axis. Instead, it's going to be deflected. It's going to have this actual path where it's going north, it's going north. It's still relatively going north in a straight line, but the Earth beneath it has moved. And it's going to appear as though it moves in this deflected pattern. That is what we call the Coriolis effect. The Coriolis effect is where the wind moves in an eastward direction as it moves from the equator up to the poles because it's deflected, or because it is because the Earth itself is moving underneath of the air that's trying to move north, right? So the air is moving north, the Earth is moving under it, so the air from the surface of the Earth is going to appear to move in that that eastward pattern, that northeast pattern. So one other thing that creates global wind patterns um, are global convection current cells. So they have the Hadley cells, there is the mid-latitude cells, and the polar cells. The Hadley cells are really the ones that we're going to focus on here, but the same thing is happening for all of these. And this is all due to convection currents. So we are going to have a lot of warm air in the tropics. So let's say that right here we have lots and lots of warm air. That's the middle of the Pacific, and the air is going to allow water, the warm air is going to allow water to evaporate. That warm, moist air is going to rise where it is going to cool. One thing that you should know is that whenever you have differences in density in a fluid, the warm fluid, air in this case, is going to rise, while the cool fluid is going to sink. Because the warm fluid has a lower density and the cool fluid has a higher density. So the cool fluid will sink, cool air will sink because it's more dense, and it is therefore quote unquote heavier, even though it has nothing to do with heaviness or weight. But the warm fluid will rise because it is lower density. Something that's lower density is going to float on top of something that is higher density. And because air is a fluid, these air masses can move relatively easy and form a convection current. So getting back to our diagram, we have all this hot air down in the tropical equatorial region. Evaporate the water off of the Pacific. That warm, moist air is going to rise, and it's going to start to cool once it gets up into the higher elevations, or higher latitudes. Sorry, higher altitudes, my bad. Higher altitudes. It's going to create clouds. Those clouds are going to precipitate down rain, okay, over the tropics. But this cool air that is now dry is going to move up to about 30 degrees north, and it's going to descend. And it's going to descend as cool and very dry. Okay. And then that cool, dry air is going to warm as it moves down towards the equatorial region and then complete the cycle. Nature does not like a vacuum. You cannot have the absence of air in any of these, any of part of this system, any part of the atmosphere. You cannot have absence of air because other air will move in to fill its gap. And that's one other thing that we would experience as wind. So wind is moving south from 30 degrees north to about the equator, where it will rise again, and it will complete that cycle. Okay. Essentially the same thing is happening with the mid-latitude cells and the polar cells, except the polar cells are a little bit different because they don't have any warm inputs because it's the polar regions. So this slide is just reviewing convection currents. If you are good on convection currents, you can skip ahead, but I'm just going to reiterate what we have going on. So we have a heat source. The heat source on this case is the surface of the Earth, or the water, or whatever surface that sun is striking, and that's going to be hot. Okay. Warm air is going to rise. It is going to cool, and that cool air is going to sink, where it will come in contact with the heat source and complete that current, where it will eventually rise again. And because nature does not like a vacuum, if warm air is rising over here, it's drawing this air in towards it, which is drawing this air down, which is drawing this air over, and you have a self-perpetuating system where all the air is driving itself around due to its motion, and it does not like a vacuum. Okay. Warm fluid is less dense, so again it will rise, and the cooled fluid is more dense, so it will sink. You see these convection currents happening whether you're talking about a fluid like water, a fluid like molten rock, or a fluid like air. Okay, and to add one more layer of complexity with this, because we're talking about Hadley cells, say the equator and 30 degrees north, we have hot air at the equator that is rising, and it is bringing water vapor with it, which I will do in the darker blue. So that water vapor is going to create clouds in the tropics, which are going to precipitate down water, and it's going to descend at 30 degrees north or 30 degrees south as cool, dry air. So cool and dry at 30 degrees north and 30 degrees south. I'll reiterate this in class and show these videos, but if you were absent, you can watch these videos now. And why do I keep emphasizing 30 degrees north and 30 degrees south? Well, the reason for that is because you have these bands of deserts that are roughly 30 degrees north and 30 degrees south. Obviously, due to local topography and differences in geography, you're going to have deserts that extend outside of those ranges a little bit, but more or less we have the world's greatest deserts around 30 degrees north and 30 degrees south. Stuff like the Sonoran, Navajo, and Chihuahuan deserts in the Americas, the Sahara and Arabian deserts, and the Gobi Desert. You have the Australian outback, the Namibian desert, and then the Atacama Desert, all at 30 degrees north and 30 degrees south approximately. And again, it's because of that descending cool, dry air. Dry air is going to have very little moisture. It's not going to rain, and you're going to have deserts in these regions, 30 degrees north and 30 degrees south. Okay, so this is one way that global wind patterns can influence local climate. So if you combine both the Coriolis effect and those circular convection current cells, you get some predominant wind patterns around the planet. In the tropics, between the Tropic of Cancer and the Tropic of Capricorn, you are going to have the trade winds. And I should point out that winds always are named from where they originate. So winds are named from their origin. It's just like if you were to talk about a person. I was born in Colorado, so I am a Coloradan. If I was to move to Alaska, I would not become an Alaskan. I would still be a Coloradan. Or if I was born in France and then I moved to the United States, I'm still French, right? Same thing with these. So the northeasterly trade winds begin in the northeast, right? The southeasterly trade winds begin in the southeast. They move towards the northwest, but they begin in the southeast. The northeasterly trade winds move towards the southwest, but they begin in the northeast. These two groups of trade winds converge at the equator, and that will become important when we talk about El Nino. But they converge at the equator, and they're both heading towards the west, but they're both easterlies. So they're easterly winds. The westerlies, either in the northern or southern hemisphere, begin in the west and they move towards the east, but they are westerlies because they're moving towards the west. And then in the polar regions, we have the polar easterlies that begin in the east and move towards the west, but they're easterlies because they begin in the east. All right, that's about it for wind patterns. The wind patterns are important because they do influence climate around the world. We don't need to get into the nitty-gritty of how it influences climate in every little region, but let's talk about oceanic currents. So oceanic currents also distribute energy around the world. Winds distribute energy. You might have a low pressure system up here and a high pressure system down here, and it's going to distribute thermal energy from the southwestern United States towards the Great Lakes region. Okay, so you're going to have that distribution of energy. We also have distribution of energy in the oceans. So the reason that the poles aren't completely frozen solid and negative 100 degrees Celsius, if that were possible, is because they do have warm ocean currents that move up towards the polar regions, right? The reason that the equatorial regions are not, 150 degrees Celsius is because they have this cool water moving from the polar regions down towards the equator. Okay, so we have this redistribution of thermal energy all around the planet. Okay, and it moderates the climate. It allows the poles to not be as cold as they are, and it allows the equator to not be as hot as it could be. So the poles not as cold as it could be, the equator not as hot as it could be. All right. It should be noted that wind patterns do the same, but because the ocean is such a more massive heat reservoir than the air is, there's a lot more energy stored in the oceans. It can distribute it a little bit more effectively. Now, you probably read the term thermohaline currents or thermohaline circulation on the previous slide. That's what we're going to talk about here. So this is all driven due to thermohaline circulation. If we break down that term, thermo means temperature, and haline means salt. So these are currents or circulation patterns that are based on differences in temperature and differences in salinity. Essentially, what's happening is you'll see either the term thermal haline circulation or oceanic conveyor belt. They're synonyms. I'm going to tend to use the term oceanic conveyor belt. The oceanic conveyor belt is what you see in this diagram here. And if you were to take a molecule of water, just one water molecule from right here off of the coast of Iceland or wherever, and track its progress throughout this whole system, it could take a couple thousand years to make an entire loop. So this is a very slow system, but is a very effective system at redistributing temperature as well as nutrients and salinity throughout the oceans. Okay, so let's trace what happens. Let's just say right here in the equator. Okay, I'm going to use red to show where the hot water is going, and the hot water is going to go along the surface. The surface is going to be hot. So all the red that you see is on the surface, and it is warm. Once it gets up to the North Atlantic, something's going to happen. It's going to cool, and it's going to freeze, and it's going to make ice. So you're going to have ice up here in the North Atlantic. When salt water freezes, it does not trap the it does not trap the salt in the ice. Okay, let me repeat that because I messed up. When salt water freezes, it does not trap the salt in the ice. Most ice, even if it forms on the surface of the ocean, is going to be pretty much fresh water. Okay, it might trap a little bit of that salt, but not a lot. So it's going to be fresh water. That means that all that salt is not being trapped in that ice, so you have this salt increasing in concentration up here in the North Atlantic. Salt water, the saltier the water, the more dense it is. So as we increase the salinity of the water, we also increase its density. Meaning that this cold salt water is going to sink. Cold, very salty water is going to sink. It's going to sink because it is more dense because it's very salty. It is also going to sink because it is cold. And it's going to go down to the ocean bottom, and it's going to trace its path all the way through here, through the Atlantic, until it gets to a couple branching points. It could just end up going around and around and around the Southern Ocean endlessly, or it could get kicked out into the Indian Ocean, where it will warm up. It will get kind of trapped in this cul-de-sac, if you will, of the Indian Ocean, where it doesn't have any escape to get back to warm waters, and it will eventually warm, and it will rise. Okay, that is what we call an upwelling. When deep water will rise, we call that an upwelling. And when it upwells, it brings nutrients with it. The bottom of the ocean is where everything is going to sink down into. Everything that's dead, decaying, organic waste is all going to sink down to the bottom. And when you have these upwellings, they bring up all of that nutrients. So these are very nutrient rich. You have upwellings in many more places on the planet than the few that it's showing here because of minor local currents or smaller local currents. The one that comes to mind is the one that we'll talk about a little bit later, where you have an upwelling off the coast of the west coast of South America. But you see that upwelling here. Okay, and then this can trace around, go around back into the North Atlantic. If it got kicked out in the Pacific, it's going to do basically the same thing. Okay, so it's all really driven, a lot of this, I should say, is all really driven by up here in the North Atlantic, where you have ice being formed and that water is getting extra salty and sinking and driving this whole current, okay, this whole global distribution. So a couple other reasons why this is important. Again, first off, it's very slow, so this is going to take a very long time, thousands to millions of years, for one water molecule to go through the whole circuit. But it is very important for several reasons. First off, it moves energy from the tropics to the poles. So again, the tropics aren't as hot as they could be if this water wasn't making its way north and south and ending up in those polar regions. And it's also warming those polar regions because it's bringing that energy up to the poles. So the poles aren't as cold as they could be. It's also very important for oxygenating the deep oceans. Where you have these downwellings, this deep water formation, you have oxygen that goes down from the surface down to the bottom of the ocean, and it oxygenates the deep ocean. Oxygen is very important for any life that depends on aerobic cellular respiration. And it also creates upwellings, which are, again, very nutrient-rich waters that are coming up. So downwellings is surface water going down. Upwellings are deep water coming up. You might be asking yourself, well, why doesn't the deep water come up anywhere, and why doesn't the warm water go down anywhere? Because, right, haven't we said that that convection currents occur in any fluid? Well, not really, and they won't here for a couple reasons. First off, the heat source here is the sun, and the sun is up in the sky, and it is shining down on the surface of the water. That means the surface is going to be warm. When you have warm water on the surface, it's just going to stay there on the surface because it's less dense than the cool water that's way down deep. So there's going to be no convection current forming because of that. There is also a difference in salt content. So you have cold, very salty water down here and less salty up at the top. And that less salty water is going to essentially ride on top of that cold, salty water because, again, salty water is more dense and less salty water is less dense. So there's going to be no reason to have a convection current here. And then you also have what is called a thermocline. This thermocline is a rapid decrease in temperature within a very short distance. So we have depth or distance here on the y-axis, and then temperature increasing on the x-axis. And we have an area that is like 22 degrees Celsius and an area that's about 6 degrees Celsius, and they're only separated by about, I don't know, 500 to 750 meters. That's a very short depth. And when you have such an extreme of cold and hot waters, they're going to resist mixing with one another. So they're not even going to mix in this region of the thermocline. And it's going to just exacerbate the whole thing, where this is going to get warmer and warmer and warmer as it's sitting underneath the sun. This is going to get colder and colder and colder as it's sitting down at the bottom of the ocean and not being exposed to the sun. So you really need those key places on the planet where the oceanic conveyor belt goes up and down to create those upwellings and downwellings. All right, this next stage is just about El Nino and La Nina, and this is more or less totally unrelated to what we were just talking about with the oceanic conveyor belt, with thermohaline circulation. So this is just another way that that global or even regional oceanic and wind patterns can affect global climate. Okay, so this whole system is part of the El Nino Southern Oscillation Cycle, or ENSO, and this is where you have changes in sea surface temperature and the equatorial Pacific Ocean. So we're looking at the equator and we're looking at the Pacific Ocean specifically. Okay, and again, it causes changes in both regional and global weather. So before we talk about what happens in an El Nino year, let's talk about what happens in a normal year. In a normal year, you have the Pacific trade winds, and the Pacific trade winds, the northeasterlies and the southeasterlies, are meeting here in the equator, and they are driving this whole system. It's what's in green. I'll do mine in green also. It's what's in green on this diagram. Okay, so you have the trade winds, the easterlies in both cases, the northern and the southern. Okay, and they are pushing from the east to the west. Okay, so east and west. And when they're pushing, those winds are literally pushing the surface of the ocean over there. So imagine that the ocean is just a pool and it's very still and it's staying underneath the sun all day. It's going to warm pretty evenly. But if you get strong winds that are pushing in one direction, it's going to push all of that warm surface water towards the direction that the wind is pushing it. Okay? Nature doesn't like a void, so to avoid a void, you have an upwelling occur on this side to replace that warm surface water that has been displaced. Okay? All of that warm surface water ends up in Southeast Asia, Northeast Australia, and it's going to all evaporate up. So evaporate, 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 and it's going to rain down in those regions. As it does so, it's going to cool. It's up in the top of the troposphere, and it is very cold, and it's going to move back and replace itself down on the easterly side. Okay? That's going to lead, one final thing, that's going to lead to relatively cool and dry in Western South America, places like Peru, Ecuador, and relatively cool, right? We're talking about the equatorial region, so it's not going to be cold, but it's going to be relatively cool. So if we look at a La Nina, this is one of the phases of the cycle. This is the cool phase. This is basically just intensifying those normal conditions. So let me repeat those normal conditions. You're going to have the trade winds, both the northeasterlies and the southeasterlies, both converging in the Pacific Ocean at the equator and pushing that warm water, that warm surface water, over towards Southeast Asia and Australia, where it is going to rise, or the air is going to rise at least. It's going to, warm up and rise and take all of the evaporated moisture with it, and it's going to rain down here in Southeast Asia and Northeast Australia. As it gets to the top of that convection current, as it gets to the top of the atmosphere, it's going to cool, and it's going to move over and complete the circle of that convection current in the air. In the water, you're going to have this warm surface water getting pushed over towards Australia and Southeast Asia. And it's just going to pool there and stay as warm water as it evaporates, and it's going to, just stay there, except for what evaporates. But you're going to have a displaced mass of water that needs to be replaced from somewhere. Where does it get replaced from? It has to get replaced from the deep. And that deep ocean current brings together all of the nutrients from the deep. Those nutrients sustain the food web that's there. They provide lots of nutrients for the phytoplankton that are there, which provide nutrients, which provides primary productivity for the entire food chain. So that you have, the small fish, the big fish, the whales, all of the marine mammals that are really famous for being off of the west coast of South America. Okay. So some global effects of this, you're going to have some of La Nina, you're going to have some stronger equatorial winds, so those Pacific trade winds are stronger. That's going to cause a weaker jet stream up in the northern hemisphere. So if you're familiar with the jet stream is moving, if I can just show on this diagram, let's show it in a different color actually. Let's do black for the jet stream. It's moving with some fluctuations up around there. So that jet stream is going to be weaker, and that jet stream is what brings us in Colorado a lot of our weather. Okay. So weaker jet stream, you're going to have temperatures above average in um, Southeast Asia and Northeast Australia, but you're also going to have it lower than average in the northwestern United States and temperatures above average in the southeast. Okay, actually all this is on the next slide, so let me just move over to the next slide. In North America, for La Nina, what you're going to have is cool and wet northwest. So you see that right there. Um, Warm and dry southern United States, both the southwest and the southeast, and then some pockets of wet here and there. In South America, it's going to be cool and dry on the western side, but it's going to be cool and wet in the Caribbean side. Okay. In Southeast Asia, India, Oceania, you're going to have lots and lots of rain. So you're going to have your seasonal monsoons, you're going to have typhoons, and they're going to end up with wetter than usual seasons. Okay. You guys do not need to know all of the global impacts, but you should know that there is global impacts. Okay. I have not seen a test question where they will say, in a La Nina year, what would the weather be like in, South Africa, for example? They're not going to ask that. But they do want you to know, and they will ask questions about it being a global system, and that you should know that it does influence the planet globally. Okay, so El Nino, let's talk about this one. El Nino is the warm phase. This happens every 3 to 7 years, but as you can see, it's kind of random. There's some breaks without it. There's some times when there's a lot of them in a small set of years. So it happens every 3 to 7 years, but it's not like clockwork. Okay. What this is caused by is a weakening or even a reversal in the Pacific trade winds, which is really weird. But let's just go with a weakening. If the Pacific trade winds weaken, if these Pacific trade winds are very weak, so they are not going to push, I'm just showing little tiny arrows because they're weak. They're not going to push that warm surface water all the way over into Southeast Asia and Australia. You're going to have a equal distribution of warm surface water pretty much throughout the equatorial Pacific region. That's going to cause a number of different things. First off, it's going to cause a high pressure system over here in Southeast Asia and Australia, which is going to lead to dryness. And you're going to have a low pressure system over here in the west coast of South America, and that's going to lead to rain. Okay, so you get heavy flooding and raining during El Nino years in those countries like Ecuador and Peru. Okay. You also tend to get a lot more rain in the central Pacific, which does nobody really any good because it's just rain right into the ocean. One other thing that doesn't happen are these cold upwellings. They are not going to upwell because all of this water is not moving towards the west. So because that water isn't being displaced, this cold upwelling doesn't have anywhere to go, so it hits that thermocline and it just goes back over and just hangs out at the bottom of the ocean. It never goes up. So I'm going to draw an X through that because it never goes up during El Nino year. Okay, so you lose those fishing grounds. If you are a fisherman in Peru, not only are you getting rained on and having heavy flooding, but now you lost all your fish, all your income, and your food source. Okay, so global effects of El Nino. In North America, you're going to have a warm northwest, warm and dry. You're going to have a wet southern United States. Okay, in South America, again, flooding rain in Ecuador and Peru. You are also going to have the rest of South America being relatively dry. You are going to be pretty dry over here in Southeast Asia. The monsoons are not going to come, and it's going to be kind of a bummer year, right? All of this is going to be warm and dry. So the seasonal monsoons are not going to come when they should. All right. So some local effects of El Nino. I mentioned the upwelling that occurs on the west coast of South America. So this is, if that is South America, we have the Galapagos Islands right there. We should have a cold current that's bringing nutrient-rich water from the deep to those areas. And again, that kickstarts the entire marine food chain. And these are some typically very productive waters. When you have an El Nino year, those really productive waters get starved of nutrients, and they don't. You have really devastating years for anything that relies, well, for everything on the food chain, right? The algae, the phytoplankton, do not have a huge population increase. They stay at low population, which means that you can only have a few small fish eating them, which means that you can only have a few big fish eating the small fish, and a few marine birds and mammals eating the small, medium, and large fish. The entire food chain can collapse if you have it, if you lose all of those nutrients. Okay, so those lack of nutrients can lead to population crashes of the producers, which causes ripple effects or cascading effects, trophic cascades throughout the entire food web. So the particular severe El Nino 1982 to 1983 led to the death by starvation of almost every Galapagos fur seal pup under the age of 3 years, as well as 3/4 of the penguin and cormorant populations. So these populations can be decimated by just something as simple as the Pacific trade winds weakening or reversing, which causes the El Nino effect. And again, this is just one example from one small little corner of the world. These climatic patterns have global impacts. So just to return to our learning objectives, again, we're talking about the Earth systems and how they result in a state of balance over time. But again, as we change things, balance gets disrupted. All right. You guys should be able to explain how environmental factors can result in atmospheric circulation. So think about warm water, or warm air and cool air, and how they create those convection currents, and as well, which result in the Hadley cells, the mid-latitude cells. You should also be thinking about the Coriolis effect. Okay, how all of that plays into atmospheric circulation. And obviously we just scratched the surface of this, it gets way more intense. All of this though is driven by sunlight. So that's where the equatorial regions are hotter, and that's why they have warmer air. And then, obviously polar air is colder, and there's going to be those differences in temperature and density. Okay, so those density differences result in convection currents. All right, over here with El Nino and La Nina, most of the Earth's atmospheric processes are driven by input from the sun, just like we just mentioned. Describe the environmental changes and effects that result from El Nino or La Nina, and those are both, again, part of the El Nino Southern Oscillation Cycle, or ENSO. So we talked about each one individually and how they result from changing oceans, changing Pacific trade winds, and the global effects that they can have. All right. We also touched a little bit on how they're influenced by geological and geographic factors, but realistically, they're mostly influenced by the trade winds. And we're not really going to get into this, and I've never even seen an AP question that is based on that. There's nothing that I have seen that talks about how El Nino is influenced by any geological or geographic factor. It's really influenced by those Pacific trade winds. Okay, but they do definitely affect different locations in different ways.